Okay, hi there, Dr. Matthew J. Trom here. This is another video in the compressible flow module where we're going to talk about the equation of state and use it to derive Mach number function stagnation property equations for flow where compressibility matters. So in a previous presentation, we talked about the onset of compressibility being at a Mach number of about zero point 0.3. And what happens when the onset of compressibility occurs is that whereas for incompressible flow, pressure, kinetic energy, and potential energy were the only three energy types that could be exchanged within the flow field, all of a sudden now internal energy, which is embodied as the temperature of the fluid, provides another source of energy that could be interchanged with the other three. And as a result, the density of the fluid can change as temperature energy is being kind of interchanged with the other three types. And so this is so-called compressible flow. And now, instead of having three unknown variables, we have five unknown variables: pressure, velocity, potential energy, density, and temperature. And so we're going to deal with now five unknowns by taking the three equations that we had for incompressible flow, which is conservation of mass, conservation of momentum, and conservation of energy embodied in the Reynolds transport theorem, and we're going to add to those three equations two additional equations to get us five equations to handle five unknowns. So the first of those two new equations is the thermodynamic equation of state for our fluid of interest, and then the second one is the process path. The thermodynamic process path that the fluid takes as it's moving from one location to another location in the flow field. Now, remember that for flows of flows of Mach number 0.5 or greater is a situation where compressible flow matters, and all of a sudden you have to start worrying about variable density and variable temperature, because the speed of sound is what governs the Mach number. The speed of sound in liquids is incredibly high, and so it's very difficult for objects or for the flow itself in a liquid to reach Mach number of 0.3. But in a gas like air, Mach number of 0.3 is much more typical. And so we're going to only focus on compressible flow in situations where the fluid of interest is air. And we're going to then use the ideal gas law as our equation of state. And because we're using the ideal gas law, there's a number of simplifications and corollaries that sort of spin off from that, which I'll talk about in a little bit as we start tackling the energy equation and the process paths for compressible flow. So just as a reminder, the thermodynamic version of the ideal gas law is PV equals MRT. Pressure times volume is equal to mass times the gas constant times temperature. And we are going to work on this to extract density. And so I'm going to divide both sides by mass. And I'm going to note that volume over mass is 1 over density, and so I'm going to take density to the other side of the equation, and I'm going to be left with pressure is equal to density times R times T. So that's my fluid mechanical version of the ideal gas equation. I'm also going to remember that for an ideal gas, provided the temperature doesn't change by very much from one state to another state for a fluid undergoing a process, that the change in internal energy of an ideal gas is just the specific heat at constant volume times the temperature change, and the change in enthalpy for an ideal gas is the specific heat at constant pressure times that temperature change. And so this table just puts into words all of the different variables that we'll be dealing with as we walk through these types of problems. So now we've got our equation of state, and we've got a couple of definitions for specific heat at constant volume and specific heat at constant pressure. The values for those constants, by the way, are 718 meters squared per second squared Kelvin for CV and for Cp, it's 105 meters squared per second squared Kelvin. Those are values for air. And then R, which is the gas constant, is just Cp minus Cv, and the value of R for air is 287 meters squared per second squared Kelvin. Taking Cp and dividing by Cv, we get the specific heat ratio, and for air that ratio is about 1.4. So those numbers turn out to be important later as we start plugging them in to the equations that we develop from the ideal gas equation of state, energy conservation, and these corollary relationships. Okay, so to start thinking about compressible flow in a flowing gas, we're going to make a couple of simplifications. So remember, we needed both the thermodynamic equation of state, which is ideal gas, and information about the process path to add two new equations to the three that we originally had to deal with these five unknowns. And so the process path that we're going to select is a process path that's both isentropic and adiabatic. So what does isentropic mean? An isentropic process is a process where the entropy is constant. Now, typically, that means that no entropy is generated and no energy in the form of heat crosses the system boundary. But there is a specialized type of adiabatic process where you are generating entropy and you are dissipating heat across the system boundary at exactly the same rate at which the entropy is being generated. And so the process is still a constant entropy process, even though you have entropy generation as the process is ongoing. So we also have to add an additional requirement that this process is adiabatic, which means there is no heat transfer. So the combination of an adiabatic process and an isentropic process tells us there's no heat transfer across the system boundary, the entropy is constant, therefore no entropy is being generated, and the process is therefore thermodynamically reversible. Okay, so given kind of that process path information, we can now combine mass conservation, momentum conservation, and thermodynamic laws under the assumption that the flow is adiabatic, isentropic. Any sort of pressure wave propagation is so-called weak. That means it does not have enough energy to exceed the speed of sound in the flow or in the fluid. The pressure wave is one-dimensional and it's propagating through the fluid. And so by applying mass conservation and momentum conservation on a propagating wave in the fluid with all of these built-in assumptions, we come to the conclusion that the speed of sound, which again is also the speed of that wave's propagation through the fluid, is equal to the partial derivative of P with respect to the partial derivative of rho, pressure versus density, at constant entropy, all raised to the 1/2 power. And that expression I won't derive for you, but you can find in a textbook, and it can be shown again just by conservation of mass and conservation of momentum applied to a system boundary which contains only this pressure wave propagating through adiabatic, isentropic, one-dimensional fluid and propagating through at the speed of sound without any additional energy. There is then from thermodynamics a Maxwell relation, which again I won't derive for you, you'll just have to take my word for it, that allows us to relate this differential at constant entropy to a similar differential at constant temperature. So it's going to be K, which is that ratio of specific heats, multiplied by partial derivative of P versus partial derivative of rho at constant temperature raised to the 1/2 power. So that's what we'll use as our expression for the speed of sound, the speed of sound wave propagation, the speed of energy propagation in this fluid, given this process path information and all of these underlying simplifying assumptions for an ideal gas. Okay, so we're going to take this expression and then we're going to take our equation of state, which again is just the ideal gas equation, and we're going to carry out this mathematical function on the ideal gas equation to figure out what this derivative actually is, right? So remember that for a thermodynamic ideal gas, the pressure is just rho RT. R is a constant and T is a constant because we're taking this partial derivative at constant temperature. That's why we use the Maxwell relation to get it from constant entropy to constant temperature. And so if I just take the derivative of P with respect to rho of rho RT, I just get RT, right, which is a constant. And so I can then take RT, I can plug it into my derivative here, and I'm left with the speed of sound is equal to the square root of KRT. So that's where this expression that I've shown in a previous presentation actually comes from. That's how it's derived. And I know that R for air is about 287 meters squared per second squared Kelvin. And I know that for air, the specific heat capacity ratio is about 1.4. So all I need to know then is the temperature of the gas, and I could figure out, or the temperature of the air, and I can figure out what the speed of sound is in that air. So I say down here, speed of sound in air is a function of temperature only. Okay, so just by way of example, what's the speed of sound in air if the air is at 300 Kelvin? Okay, so I take my 1.4 K value, my 287 meters squared per second square of Kelvin R value, and my temperature at 300 Kelvin, plug them all in, take the square root, and I get about 347.2 meters per second. Now, a follow-on question, a practical follow-on question might be, given that we know from previous lectures and presentations that Mach number of about 0.3 is the threshold at which compressibility effects need to start being considered, what speed of an object in air or speed of air itself, if the air is at 300 Kelvin, is the threshold that we have to start worrying about these compressibility effects. And so I'm going to take my my Mach number, which is the velocity over the speed of sound, recognize that that value of about 0.3 is the point where I have to start to be worried about compressibility effects. Then I'm going to multiply by the speed of sound in air at 300 Kelvin, which, as I calculated before, is 347.2 meters per second, and I get about 104.2 meters per second. So at about 300 Kelvin, 100 meters per second or higher is the velocity threshold, the speed threshold at which you have to start worrying about compressibility effects. Okay, so now that we've got the speed of sound derived, let's talk about the ideal gas isentropic relations and the energy relation. Now, I won't derive these because this would have come from a thermodynamics course, but for an isentropic process, again, a constant entropy process, there are a number of very, very nice, clean, mathematically beautiful relationships that relate pressure ratio at two states to temperature ratio at two states to density ratio at two states, and these are those relations. Again, the derivations can be found in a thermo course. Remember these because we'll come back to them and use them later. I'm also going to now look at the full-blown first law of thermodynamics for an open system made up of air. And so here is the first law of thermodynamics for an open system, and I'm going to apply to it the same assumptions that I applied more or less to my propagating pressure wave here, which is that whatever system I'm interested in is adiabatic, meaning no heat transfer. All of these Q terms then go away. There's no shaft work, meaning all these W dot terms go away. Mass conservation, that M dot in is equal to M dot out. And so the mass terms are going to cancel with each other. And then finally, that any potential energy change as a result of elevation in the flow field is going to be very small compared to the enthalpy and the kinetic energy. And so this GZ term and the inlet and GZ term on the outlet are ignored because they're small compared to V squared over 2 and compared to H. So under those assumptions, my first law of thermodynamics for this open system breaks down into just H plus V squared over 2N is equal to H plus V squared over 2 out. And if I take that relationship and I then consider it across some sort of thermodynamic process represented by state 1 and state 2, I just get that h1 plus v1 squared over 2 is equal to h2 plus v squared, v2 squared over 2. And it turns out that those are constant, right? Like, in other words, the combination of enthalpy and kinetic energy doesn't change from state 1 to state 2 for this process with all these assumptions built in. And so I'm going to define this thing that I call stagnation enthalpy, which, if you think about what stagnation enthalpy represents, it's just the enthalpy of a flow field if that flow field is brought to rest adiabatically, right? In other words, I've got some enthalpy, I've got some kinetic energy in my flow field, and if I then bring that flow field to rest, that is, drive the velocity down to zero, and I do that in a way that preserves the assumptions that I use to get my first law energy balance from this state down into this state, which is adiabatically, that is no heat transfer associated with that slowing and that stopping process, then I end up with this constant, again called stagnation enthalpy. And we'll see later on why this is important. But at the moment, just be aware that it's a constant that represents the total enthalpy in a flow field, even if the flow is moving, right? In which case we've got both the real enthalpy and then the kinetic energy. And I'm just going to take that kinetic energy, dump it into the enthalpy, and that gives me the stagnation enthalpy. Okay, so also for an ideal gas, we have the identity that the enthalpy is equal to the specific heat at constant pressure times the temperature. And so I'm going to take this identity and I'm going to plug it into the expression here that I have above, recognizing then that h1 plus v1 squared over 2 is equal to the stagnation enthalpy, also meaning that Cp times T1 plus v1 squared over 2 is equal to Cp times T naught, where T naught is now the stagnation temperature. So by initially creating this thing called stagnation enthalpy, we can start to spin out other stagnation properties, and those properties include things like temperature, stagnation density, stagnation pressure, and so forth. Then I can say, okay, now that I've got this relationship for the temperature in my fluid at any state 1 being equal to Cp times the stagnation temperature, I can divide both sides by temperature and come up with a ratio of the stagnation temperature to the actual temperature at any point in the flow field by solving for that ratio. And so that's what I do here in this step. So I've now got the stagnation temperature is equal to the temperature at some point in the flow field. The ratio of those two, temperature, stagnation temperature divided by temperature at any point in the flow field, is equal to 1 plus the velocity at that point in the flow field squared divided by 2 cpt. Now at this point, I'm working towards something that's very useful here potentially, right? Because if I've got this expression that relates the stagnation temperature to the temperature, just based on the velocity and the temperature of the flow, I can work on this a little more and come up with an expression for the stagnation temperature per temperature at any point in the flow field, right? So that's what I'm going to do. And the first thing that I'm going to do is start to work on my original expression for the speed of sound in my gas, right? Which, remember, the speed of sound is just the square root of kRt. If I square both sides, I get the square root of the speed of, or the square of the speed of sound is equal to just kRt. And now if I divide top and bottom by k minus 1, and you'll see why in a second that I want to do that, divide top and bottom by k minus 1, I get a squared divided by k minus 1 is equal to kRt divided by k minus 1. And it turns out that kr divided by k minus 1 is actually Cp. And I'll leave it up to you guys, given the definition of Cp, R, and Cv that I gave before, to sort that, and K, to sort that out on your own. But given that identity, I've now got a way to relate KRT over K minus 1 to CPT. And CPT is living right here in the denominator of this expression. And so I'm going to now substitute CPT for KRT over K minus 1. Stick that in there. And recognize that KRT is a squared, right? And so my expression then becomes stagnation temperature divided by temperature is equal to 1 plus V squared divided by 2 multiplied by K minus 1 divided by the speed of sound in the fluid squared. Now, something incredibly magical and wonderful has just happened here, right? I've got a velocity squared in the numerator. I've got the speed of sound squared in the denominator. And so what can I do? I can bunch those together and turn them into the Mach number squared, right? Because the velocity of the flow divided by the speed of sound of the flow is the Mach number. And so I can just rearrange through algebra and get my ratio of stagnation temperature to temperature being equal to 1 plus K minus 1 over 2 multiplied by the Mach number. So this is now incredibly useful and incredibly powerful because all I need to know to find the stagnation temperature is the temperature at any point in the flow field and the Mach number at that location in the flow field, and I can work out what the stagnation temperature is. And as we'll see in follow-on lectures, the stagnation temperature turns out to be quite useful for finding, other values and other properties of interest. The first one is to take those ideal gas isentropic relations that I described before. Remember, I didn't derive these. I just asked you to accept that they're true and reminded you that you can find them in a thermo lecture or a thermo textbook. And I'm just going to plug in T naught over T, and I'm going to solve for the ratio of pressures and the ratio of densities. And so here's my Mach number function stagnation property relation for temperature, which I derived before. And now using those isentropic relations, because again, remember, I've assumed that my process is isentropic. That's the process path. So I've used that to assume that the flow is isentropic. I've now got a ratio of stagnation pressure to pressure in the flow field, which is just this guy. And I've also got the ratio of stagnation density to density somewhere in the flow field, again, just as a function of Mach number, which is this guy. And so these equations are all very, very powerful for the same reason that I described before, in that now you can find the stagnation temperature, the stagnation pressure, and the stagnation density in a flow field just by knowing the temperature or the pressure or the density and the Mach number at that same location in the flow field. And once you know one of these, you know all of them, right? Because you can take these relationships and you can use them to find the relationship between pressures and densities, for example, if you know temperatures, or vice versa. So by combining, again, mass conservation, momentum conservation, the energy equation, thermodynamic equation of state, the ideal gas law, and the process path, which is this assumption of an isentropic adiabatic process, I now have an enormous amount of really useful information that I've gleaned from those 5 equations that basically tell me almost everything that I need to know about this fluid, this flow field that's operating at Mach number of above 0.3, where compressibility effects matter. So that brings us to the end of this particular presentation for the compressible flow module. Thanks for your attention, and look forward to seeing you guys in future lectures. Bye.